All right, and we're live.
And we'll do it live. Upside down.
That's right. Matter of fact, goes, respectfully, I say to thee, I know that you're cheating. I wouldn't say that respectfully to him. I'd be like, you know, throwing things at him. All right, so let's talk about the.
It's on the Instagram for you almost.
Yeah, that's good.
That's really good. That was really good.
So the piece that is, well, the piece that is e to the minus b, e to the minus 1/2, e to the minus e over kt. So remember this piece, the first piece there, comes from the barrier penetration probability. And the second piece is just the Maxwell-Boltzmann distribution in terms of energy. Exhibits a peak called the Gemolf peak. A peak, a maximum. Energy E naught equals bkt over 2 to the 2/3 power. It's easy to show that. You just set the derivative equal to 0 and solve for E to find the location of the maximum, and you get bkt over 2 to the 2/3 power. As you joyfully show, yes. Which implies that the greatest contribution to the integral comes from a fairly narrow range of energies. And over there on the screen is the illustration of what is going on. Figure 10.6 from your book, 10.6. Let's allow our guest to see figure 10.6 on the screen there. So it's got both of those factors plotted. So this is the e to the minus e over kt term. So which one is that? That's the Maxwell-Boltzmann, right? So this is on the tail of the Maxwell-Boltzmann distribution, the high energy tail of the Maxwell-Boltzmann distribution. It exponentially decays. The probability rapidly gets smaller of finding particles of a given energy after you're past the peak of the Maxwell-Boltzmann distribution. And then meanwhile, the barrier penetration probability, that increases as the energy increases. The faster they're going, the easier it is for the tunneling to happen because they get closer to one another, so there's not as much distance they have to tunnel through in order to feel the strong nuclear force and get together. And so notice then you've got one term that's decreasing with energy, another term that's increasing with energy. To make it visible, by the way, that term here, the e to the minus b, e to the minus 1/2 term is multiplied by 1,000, so that it would look okay on the same plot. And so it's the product of the two that times SCB is giving the contribution to the integral. And so since one's decreasing, the other's increasing, there's a happy medium where there's a peak. So here's the gamma peak E naught for conditions inside the sun. So it says this particular example it represents the collision of two protons at the central temperature of the sun. So they plugged in like 15.8 million Kelvin or whatever, central temperature of the sun, and calculating all this. So there's the peak. Notice it's at an energy of about 6 keV, which is actually rather small. So a limitation on our ability to study reactions inside stars is they're difficult to reproduce in the library. They are, that's a good thing, in the laboratory, because if you fire a proton at 6 keV energy at another proton, it's going to be like, you're kidding. They're never going to fuse in the laboratory at those kinds of energies. So it's difficult to measure the cross sections because the typical energies at which the reactions take place in the sun's core are very low compared to what it would take to get a significant probability of fusion in the laboratory. So what's making up for it? Why is it working inside the sun but not in the laboratory at these energies which are way too low for there to be a very high probability of nuclear fusion? Because clearly, the faster they're moving, the higher the probability of fusion, but the problem is there's hardly any protons with energies of 10 keV, much less in the MeV range, which is more like the height of the Coulomb barrier. So there's hardly any protons in the energy range where there starts to be a really significant probability of fusion. Most of the protons that are fusing are doing so at energies where the probability is very low. So what's making up for the low probability of fusion for each pair of nuclei? The center of the sun has lots of nuclei, right? Lots of nuclei, way more than you can make up for in the laboratory. And this is related to, remember what the average time for one proton to fuse inside the sun was? In the first step? About 7 billion years, 7 billion years. So if you fired protons at 6 keV in the laboratory, if you did it one proton at a time, whatever, it's not quite the same as what rate you're firing it at. But in other words, it's a very low probability. But in the sun, that dominates because there's so darn many protons around that even though each one lives a long time, has a very low probability of fusing on any given approach to another proton, there's so many protons around that some of them are always fusing, is what it comes down to. So it's a little bit inconvenient that, that the energy is so low from the standpoint of being able to make measurements in the laboratory that then translate into what's happening inside the stars. On the other hand, the conditions inside the stars are allowed us to exist in the first place, so it's not something to complain about in the end. By the way, the curve showing the animal peak, by the way, has been multiplied by 1,000,000 in order to make it visible on the plot. It's really, right down here, hardly if you were to see it if they hadn't multiplied by the term. So, any questions? So, yay tunneling, yay having a lot of protons in the sun, all that sort of thing.
Okay.
And there was much rejoicing. Yay. Just like in E&M today. Oh, you should have seen it. They were just like, I couldn't believe how enthusiastic they were again.
We're going nuts.
Oh, yeah.
This is going well.
That's right.
If I go home, that means that the biophysics paper will be there waiting.
That's true.
So if I never go home,
It'll still be there.
it'll still be there.
Yes.
I will be there.
You just won't be there.
I might have to make more Instagrams. Oh,
If you just go actually home to California, I feel like this never happened.
I remember like had to work on a paper. My finally like followed me home. It was
Wow.
an escape.
That's not good.
It was really unfortunate.
So in the end, we're trying to write expressions for epsilon, the energy generation rate. We usually write it in terms of the mass density rho instead of the concentrations, instead of the number density. So the number density, like n sub I, the number of I nuclei per cubic meter, well, that would be the density times the mass fraction of I, the percentage by mass of I, divided by the mass of species I. In other words, this is saying total density times the fraction of it that is species I will be the number of kilograms of species I per cubic meter, divide that by the number of kilograms per particle of species I, and that'll be the number of particles of species I per cubic meter. Kilograms per cubic meter divided by kilograms per particle is particles per cubic meter. So that xi there is mass fraction of species I.
So we can just call the numerator rho I.
You could, yeah, you could call it rho sub I if you meant that to be the density of species I. It is the same thing, yes. But astronomers like mass fractions, as you know, right? Your x's and your y's and your z's. So why stop now, right?
You're gonna stop there.
So NINX will then be proportional to, this is a fish, proportional to rho xi, rho xx. And there's the m's in there too, which is why it's proportional instead of equal. So you got rho squared times the product of the two mass fractions, Si and Xx. And we found an expression for RIX, which is number of reactions per cubic meter per second. But remember, we like epsilon, which is energy per kilogram being generated per second. Or in other words, epsilon is going to depend on, you still have to multiply by the energy per reaction, but epsilon depends on the number of reactions per kilogram per second. So we divide RIX by rho to get that epsilon is proportional to just 1 power of rho times xi times xi.
Thank you.
So reactions per cubic meter per second depends on rho squared. But if you want it per kilogram per second, you're dividing by rho to convert, and so it's just rho times x out of x for absolute thing that we like. All right, now here comes some craziness. Oh, our guest has been staring at the screen the whole time. Sorry about that, guest. Here, allow me to have you stare over here at the board again, and please feel free to pause the video while you're staring at the board over there. But we're just going to continue. So when you hit play, you're going to hear what I just said. We're just going to continue. And then you'll hear it again because I said we're just, no, it's on a loop. It's on a loop, that's right.
And we're just like,
Yes. A factor we haven't accounted for is electron screening. Which reflects the fact that free electrons partially shield the positive nuclei from one another, reducing their mutual repulsion and thus enhancing the reaction rate. Electrons between the two nuclei keep them from seeing their full positive charges, and so they actually help the reactions proceed by making the nuclei not repel as much as they otherwise would without the electrons around. Electron screening, which reflects the fact that free electrons, as opposed to the expensive ones.
the best things in the world are free.
That's true, yes. Partially screen, we call that, the positively charged nuclei from one another. So they're like a screen between them, making it harder for them to see their positive charges, if you will. Reducing their mutual repulsion and thus enhancing the reaction rate. Damn, I thought playing the song would get the earworm out of my head when I was starting to whistle. Which is
Nope.
it's a
We need
small
something else to catch
world.
it.
What?
We need something else that's catchier.
I know, that's why I started going, it's a small world. Except the problem is, don't replace an earworm with a worse earworm. So,
It's the only way. We have to go out a little deeper.
yes. I'll level down further into hell.
Yeah. Out of 10 levels of hell.
Mhm.
Level 5.
it should be 2 level I plus n, no, it should go to 0. So it'll be
The
fine.
limit does not exist.
Starting with the reaction rate integral. Epsilon for the combined PP chain, you know, all the different branches together. is calculated to be epsilon sub pp is 0.241 rho x squared fpp psi pp cpp t sub 6 to the minus 2/3 e to the minus 33.80
Is it minus 2/3 or minus
thank you, 2/3, yeah, I said T6, so I have a 6 in my head. E to the minus 33.80, T6 to the minus 1/3 power watts per kilogram. Isn't it beautiful? T6 is the temperature in multiples of a million Kelvin. So in other words, if the temperature is 13 million Kelvin, T6 is 13, for example. I'm going to say that in a second, but that's what you're probably wondering. This is the kind of expression that ASTR uses to calculate the energy generation. Where T sub n is, by definition, T over 10 to the nth power. So T6 is the temperature divided by 10 to the 6th, for example. Sub Pp, which is a function of the mass fraction of hydrogen, the mass fraction of helium, the density, and the temperature. It's approximately 1 for the pp chain, doesn't do much. Psi pp, which in general is a function of the mass fraction of hydrogen, the mass fraction of helium, and the temperature. Well, it's actually approximately 1 as well for the proton-proton chain. It's a correction factor accounting for the simultaneous occurrences of pp1, pp2, and pp3. Three different branches. And CPP involves correction terms of higher order in the inverse of the temperature. I know this is all very helpful in understanding it. Because it's like, yeah, where did it come from? I don't know either. Correction terms. Higher order in the reciprocal of the temperature. As you will joyfully discover in doing the homework, near T sub 6 equals 15, around 15 million Kelvin, which is about the sun's central temperature. This can be approximated via the power law expression Then epsilon pp, the generation rate per energy generation per kilogram, energy generation per, the rate per kilogram of the pp chain is approximately epsilon naught prime pp, a constant out front, times rho x squared times psi pp fpp times, the really important part is T6 to the 4th power. Where epsilon naught pp prime is 1.08 times 10 to the minus 12th power watts per cubic meter per kilogram. Or watts cubic meters per kilogram. So 10 to the minus 12 watt cubic meters kilograms inverse for the units of that. So why is it capital X squared right there? Why is it the square of the mass fraction of hydrogen showing up there? What are the two species that start out for the proton-proton chain?
It's hydrogen and,
Hydrogen and hydrogen, right? In other words, it's hydrogen fusing with hydrogen. This is hydrogen fusing with hydrogen. So XIX is X times X is what it comes down to. I and X are both hydrogen in the first step. Is why that shows up. XIX is X times X. So Xi equals XX equals X is just the fraction of hydrogen. Just be a capital X right there. So note, the nuclear reaction rate is very sensitive to temperature. It goes like the temperature to the 4th power. A small increase in temperature produces a large increase in the nuclear reaction rate. But if you think that's impressive, let's look at the CNO cycle. Remember, the CNO cycle also happens in the sun, but it produces about 10%, something like that, of the energy. Most of the energy is from the pp chain. We're almost there. The CNO cycle near T6 equals 15. The power law approximation is epsilon CNO is approximately epsilon naught CNO prime rho x CNO, where XCNO is the sum of the mass fractions of carbon, nitrogen, and oxygen. I'll write that down in a minute. T6 to the power of 19.9. It goes like almost T to the 20th power does the CNO cycle. Our epsilon naught prime CNO at constant out front is 8.24 times 10 to the minus 31. This time it's watts per cubic meter per kilogram squared. And I have to think about why the units digits are different this time, but I'm tired, I don't feel like it. So X CNO is XC plus XN plus XO. In other words, how much carbon, the mass fraction of carbon plus the mass fraction of nitrogen plus the mass fraction of oxygen. So the point here then is the CNO rate goes much faster with temperature than the proton-proton chain rate does. So as you make a star more massive, the core temperature goes up, and so the CNO cycle is going to start to dominate at temperatures just a bit higher than the sun's central temperature, at masses just a bit higher than the sun. Since epsilon CNO depends so strongly on temperature, at sufficiently high temperatures, the CNO cycle becomes more important than the PP chain. The transition occurs in stars slightly more massive than the sun, about 1.2 solar masses or so. I've heard it quoted as more like 1.1 solar masses, so I don't know, but it's not much. Transition occurs in stars slightly more massive than the sun. So this is an important distinction between stars in the universe today and the very first generation of stars, because the Big Bang essentially made only hydrogen and helium. Maybe it made a little bit of lithium, but it made almost nothing but hydrogen and helium. So the very first generation of stars was pure hydrogen and helium. There was no CN or O, so they didn't have CNO cycle as a possibility. And so they would have behaved different from stars today because of that. Because, first of all, for reasons that we'll talk about when we talk about star formation, they would have tended to form as more massive stars than today. And that would mean that they would live very short lives, and that explains why there aren't any of them left. We've never seen any so-called first-generation stars where you would expect to see nothing but hydrogen and helium in their spectra. Every star we've ever observed has some heavy elements. So it must be that none of the first generations of stars is still around. There's a reason for that, because it turns out that heavy elements also help a molecular cloud to cool. For that matter, yeah, they help a molecular cloud to cool, and that allows it to collapse at a smaller mass than if that did not happen. So you would need a bigger cloud to collapse into a star for the first generation of stars, because they didn't have molecules other than hydrogen to help cool them down, as we'll see. So they were massive, that would mean they burned their fuel very rapidly, they didn't live very long. And then another thing is that even though they were massive, they didn't have the CNO cycle, so that would change their interior structure compared to a star of the same mass today, as a result. The end, or is it the beginning? Astrophysics 2.
Beginning of the end.
The beginning of the end. Actually, the halftime in this case.
It's just one number.
Yeah. Break time.